Good morning. Welcome again. Let us continue with the basic concepts of engineering thermodynamics. In this session, let us learn how to calculate thermodynamic properties of systems. See, let us look at this question. State whether the system shown is open or closed when in operation. Here, there are two systems shown. One is system A, another one is system B. System A has a boundary like this, enclosing water tank, water wheel, water collecting tank. And system B has a boundary around water wheel. As we have mentioned, in a closed system, mass cannot enter into the system nor leave the system. Mass is constant. However, there can be work interaction and heat interaction. So if you consider in that principle, if you consider this as a system, into the system no mass is entering nor mass is leaving. So if you consider, probably if you put a shaft, and we can definitely get the work here. So you can call this system a closed system. Suppose if I consider water wheel alone, look here, water is entering, mass is entering into this, mass is leaving. Of course, work is also crossing the boundary of the system. This we can call it as an open system. So let us consider another example. See this IC engine. Again, state whether the system shown is open or closed when in operation. This is the boundary of the system. This is the inlet manifold. This is the exhaust manifold. There is inlet valve, exhaust valve. Air fuel mixture will cross the boundary and enter into it during the suction stroke through the inlet valve. The exhaust gases will leave the system through the exhaust manifold. So mass is entering, mass is leaving. Of course, fuel is entering, heat interaction is also there. I can take out the work from here. So work interaction is also there. So we can say this is an open system. Let us consider the next example. State whether the system shown is open or closed when in operation. That is only the cooling system of the engine you consider. This is the radiator. This is the upper tank. This is the lower tank. This portion is the engine jacket. The coolant enters over here, passes through the jacket, gets heated up. Again the hot fluid will come here, gets into the top header. As it passes through this, it cools, comes to the bottom header. Again it is pumped. Again it passes like this. Here the coolant mass, this is not, if I put a boundary, it is not crossing the boundary of the system. No mass is entering, no mass is leaving. Filler cap is closed. However, it is throwing out more heat here. It is producing work. There are work interactions and heat interactions. However, the mass of the coolant remains the same. So this you can consider as a coolant system if you consider it is a closed system, right? Closed system. Now state whether the boiler shown is open or closed when in operation. Look at this boiler. This part. liquid, that is water is entering, getting heated up, converting into steam, it's going out. Again water is entering, right? So here mass is entering, mass is leaving. So you can consider this an open system. State whether the system shown in bold is open or closed, homogeneous or heterogeneous. A mixture of oxygen and hydrogen in combustible proportion in a rigid non-conducting envelope is ignited by an infinitesimally spark, electric spark. The system is enveloped by a rigid surface, therefore it's a closed system. That means no mass is entering, no mass is leaving. However, the composition of the mixture changes from place to place as ignition advances, and therefore it cannot be a homogeneous system, so it is a heterogeneous system. Classify the following into intensive, independent of size, extensive, size dependent, intrinsic, independent of frame of reference, extrinsic, dependent on frame of reference. So let us take these properties: pressure, volume, entropy, specific volume, temperature, velocity, electric charge. So I'll list out all these properties. I've written here intensive, extensive. This is size dependent, size independent, intrinsic, extrinsic, frame of reference dependent, independent of frame of reference. So pressure, it is not size dependent, so it is intensive property. It is again not dependent on frame of reference, so intrinsic. Volume, dependent on the size, that's why it is extensive. Independent of frame of reference, intrinsic. Entropy, it is size dependent, so extensive. So it is with the frame of reference, so extrinsic. Specific entropy, it is entropy per unit mass. That's how it becomes independent of the size, so it becomes intensive property. Anyway, entropy is extrinsic, specific entropy is also extrinsic. Specific volume, again it is independent of mass, it becomes intensive property and intrinsic property. It is not frame of reference dependent. Temperature is an intensive property, it is not dependent on size. It is not dependent frame of reference, so intrinsic. Velocity is, yes, independent of size, intensive. Extrinsic because it is frame of reference dependent. Electric charge, yes, intensive. Similarly, it is intrinsic. The pressure of a gas in a pipeline is measured with a mercury manometer having one lip open to the atmosphere as shown in figure. This is the pipeline through which a gas is flowing, and we have connected a U-tube manometer. One end is connected to the pipe, other end is open to the atmosphere. P is the pressure of the gas that is flowing. P0 indicates the atmospheric pressure. Here there is a manometric fluid. When the gas is flowing through this, if the gas pressure is higher than the atmospheric pressure, it will apply a force so that it will push this manometric fluid upwards till the pressure values balance. That means if I take a reference line A and B, the pressure of the gas that is acting here must be equal to sum of the pressure of this fluid plus atmospheric pressure. So then, if the difference in the height of mercury in the two limbs is 562 millimeter, this Z is 562 millimeter. If that is the case, calculate what is the gas pressure here. So gas pressure must be, this is the atmospheric pressure plus this extra. So this we have to add. We have to find out what is the pressure here. To that standard atmospheric pressure we have to add. What is the atmospheric pressure value? Atmospheric pressure value we always read using a device called barometer. So it reads 761 millimeters of mercury. You must have heard in physics it is 76 centimeters of mercury, or 760 millimeters of mercury, or 76 centimeters of mercury. In this place the barometer reads 761 millimeters. And acceleration due to gravity here 9.79 meter per second square. You have studied it as 9.81. At this particular location it is 9.79 meter per second square. And the manometric fluid that is used here is mercury, and its density is 13,640 kg per meter cube. So what is the pressure that is acting here? That this pressure. As I mentioned, this pressure should be balanced against this. This pressure is P naught plus this one. According to hydrostatic principle, P is given by rho g z. Rho is the density of the fluid, g is the acceleration due to gravity, z is this height. Rho g h or rho g z we call it. So P naught you can call it as rho g z naught. This is what you call it as the barometric height. Rho is the density of the manometric fluid. So rho g z naught you substitute here. Rho g z is there. Take out rho g common, then you will get rho g z plus z naught. Z naught he has given 761 millimeters of mercury. Z again he has given 562 millimeters of mercury. So density of mercury is 13,640 kg per meter cube. G is 9.79 meter per second square. Z 562 millimeters. So 1000 if I divide by, then I will be getting meters. Similarly, the 761 if I divide by 1000, then I will get meters. Correct? Then this is kg per meter cube. This is meter per second square. This meter. Then if I cancel all the units, I'll get Newton per meter square, nothing but Pascal. So if I calculate, I'll get 177 into 10 to the power of 3 Newton per meter square, or 177 into 10 to the power of 3 pascals. This 10 to the power of 3 we can make it kilo, then you can call it as kilopascal. So this should have been capital P. Now this you can call it as 1.1 10 to the power of 5 Newton per meter square is bar. So you can call it as 1.77 bar. So 1 atmospheric is equal to 1.01325 bar. If I make that conversion, I will get 1.746 atmosphere. This is what you call it as the pressure that is acting at this point. Now, find out the pressure difference shown by the manometer deflection of 30 centimeters of mercury. Take local acceleration of gravity as 9.78 meter per second square and density of mercury at room temperature as 13,550 kg per meter cube. As I mentioned earlier, from fluid static principle, pressure is given by rho g h. So rho is I have used a manometer and I am measuring the pressure. The manometric fluid that I have used here is mercury. Just like this, I connected a manometer. So here, this is the fluid I am talking about. Its density is rho. That value is 13,550. G acceleration due to gravity is 9.78. And let us say this height is 30 centimeters. I have converted into meters by multiplying with 10 to the power of minus 2. So rho GH. So I'll get this many pascals. This is correct. Capital P pascals. This you can call it as, if you want, gauge pressure. Correct? So that's how you can calculate. This is from the fluid statics principle. You get P is equal to rho GH. An evacuated cylinder vessel, vacuumized cylindrical vessel of 30 centimeter diameter is closed with a circular lid. There is a cylinder, it is closed with a circular lid. Inside that cylinder, right, it is evacuated. There is vacuum present. So on this lid, atmospheric pressure is acting. So now, if you want to open this lid, we have to work against that atmospheric pressure. Estimate the effort required for lifting the lid if the atmospheric pressure is 76 centimeters of mercury. So what is the pressure that is acting on the lid? Pressure acting on the lid is nothing but 76 centimeters of mercury, and the lid is circular, it has area. That means the force that is acting on the lid is nothing but pressure into area. So force acting on the lid is pressure into area. Pressure, as I mentioned, using fluid static principle, it can be given as rho GH. Since it is a circular lid, the area is pi by 4 d square. So density of mercury, I have assumed it as 13,550 kg per meter cube. G, he has given 9.78 meter per second square. H, 76 centimeters, I have converted into meters by multiplying with 10 to the power of minus 2. So rho GH. Pi is 3.14. Diameter is 30 centimeter. I have to convert into meter. I have multiplied with 10 to the power of minus 2. So pi d square by 4. So I'll get this. This is the kind of force I should apply on the lid to open. Calculate the actual pressure of air in the tank. If the pressure of compressed air measured by manometer is 30 centimeter of mercury and atmospheric pressure is 101 kilopascal. Take G is 9.78 meter per square centimeter. Calculate the actual pressure of air in the tank. There is a tank. Inside that there is a compressed air. So what I have to do is I have to measure what is the pressure here. So pressure measured by manometer at the tank is what you call it as gauge pressure. So as I mentioned earlier, it can be given by rho GH. So mercury manometer, mercury density is 13,550 kg per meter cube. G is given by 9.78 meter per second square. That's the local value. H is 30 centimeter. I have converted into meter by multiplying with 10 to the power of minus 2. So I have got rho GH. Substitute all these things. I will convert Pascal into kilopascal. Dividing by 1000, you'll get kilopascal. This is gauge pressure. Actual pressure or absolute pressure is gauge pressure plus atmospheric pressure. Gauge pressure value is this. Atmospheric pressure is always 101 kilopascal. So add these two, you will be getting the total pressure, right? Determine the gauge pressure at a depth of 1 meter in a tank filled with oil specific gravity pointed. Take density of water as 1000 kg per meter cube and G is 9.81 meter per second square. Please, we have to measure the pressure at a depth of 1 meter in a tank filled with oil. So again the equation comes rho GH. Here I have to get the density of the oil. They have given specific gravity pointed. Specific gravity density of oil is nothing but specific gravity into density of water. Density of oil by density of water is what we call it as specific gravity. So Density of oil is specific gravity into density of water. Specific gravity already has given as point and density of water is given as 1000 kg per meter cube. So that you will get the density of oil. That value you substitute, G value you know, H value you know, you will get the pressure, gauge pressure. Calculate the gas pressure using a mercury manometer with one limb open to the atmosphere. This one, as shown in figure, barometer reading is 76 centimeters, that is atmospheric pressure. Density of mercury is given, take G is 9.81 meter per square centimeter. A gas is flowing this, you connect a manometer, the gas pressure is acting on this mercury, because of that it is rising up, so we have to find out what is the total pressure. So obviously one is the atmospheric pressure, that is rho GH, this is the density of mercury, acceleration due to gravity, H it is 76 centimeters, so you have got the atmospheric pressure. Plus what is the gauge pressure? Gauge pressure. Again it is mercury, rho density 9.2 and this is 40 centimeters. So you will get this. So if you calculate all these values, you will get gas pressure as 154.76 kilopascal. 1 kg of water falls from an altitude of 1000 meter above ground level. What will be the change in the temperature of water at the foot of fall if there are no losses during the fall? Take specific heat of water as 1 kilocalorie per kg. So now energy can neither be created nor destroyed. So it has a kinetic energy. So this kinetic energy has to be converted into some kind of thermal energy. So that's the equation I said. mgh is the kinetic energy loss should be equal to gain in thermal energy. So m is 1 kg of water. So m is 1. G is 9.81. Correct. It's not given, so I take the standard value. H, it is falling from a height of 1000 meters. So I got mgh. I am dividing this by 4.18 to convert this also into kilocalorie, because he has given this as kilocalorie. Then mcp delta t, mcp delta t, m is 1, cp, yes, 1 into 10 to the power of 3, specific heat of water, correct. He has given, take specific heat of water is 1 kcal per kg, correct, 1 into 10 to the power of 3, and temperature is delta T, right. So now by balancing this mgh and this value, by balancing this, if I calculate the unknown value delta T, I will get 2.35 degree Celsius. That is the change in or increase in temperature of water. A spring balance is used for the measurement of weight. A standard gravitational acceleration gives a weight of an object as 100 Newton. Determine the spring balance reading for the same object when measured at a location having gravitational acceleration as 8.5 meter per second square. At standard gravitational acceleration, mass is what? W is equal to mg. M is W by G. W is 100. G is 9.81. So you will be getting M. So suppose the same M, if I weigh this in another gravitational fluid whose G value is 8.5 meter per second square. So again W is equal to mg. M is, we know that value. G value is 8.5. So it will weigh as 86.65 Newton. So these are some of the simple examples I have illustrated to learn how to calculate properties of fluid. Particularly, I have dealt here with calculation of pressure values of a system. So please practice such kind of examples so that you can understand better. So for the time being, thank you. We will continue the next session.